kinetics we are saying, kinetics of the drug stability. Kinetics means it is a motion or movement. When it is a static means it is at the rest and it is not moving. Opposite phenomena is a motion and movement. Generally, any reaction according to concept Arrhenius, if they are moving, they collide with each other, the reactants, and they will be tend to form a product. This is a common concept. If any reaction required to be proceeded, that has to be moved. When they are moving, the reactants are getting hitting to each other, and the probability of reactant hitting with each other is more, rate of reaction is more. So this is actually what the concern of Arrhenius, and he has linked the same thing with the temperature. When the temperature is increasing, the movement of reactants are also getting increased, and you are going to have a better reaction rates. It means our any reactions are linked with the motion or the movement that is linked with the temperature, and most of the times endothermic reactions they linked with the temperature in a positive manner, exothermic reaction in a negative manner. But here, most of the times, whenever we are calling it as a kinetics, it is a motion or movement that is linked to the velocity or the rate. At what rate, what extent the reactants are getting interacted to get a products. In the stability, your starting material is stable in nature, but the ending material is unstable. This is what you need to look into the picture. The starting material is generally stable in nature, and the end product is degradation products in the drug stability. So the kinetics deal with the study of rate at which process occur and mechanism of the chemical reactions. So both it is linking at the what is the velocity of the reactions that is proceeding, and how they are proceeding, what is the mechanisms. In both the cases, we are going to deal in the kinetics. It involves the study of the rate of change. Most of the times, your initial drug product will be changed to the final degradation product, and the way in which the rates are influenced by the concentrations of the reactants and the concentrations of the product, and another chemical species, they may be hinder, they may catalyze the reaction that may be present, and also by the altering the factors such as solvent, pressure, and temperature, so that we will be finding a better ways to stabilize our drugs. This is actually what our concern is. Whatever we are going to study, we want to stabilize our drug product. So kinetics applied to the one is stability, so that we will be having a highest shelf life, and we can keep our product longer period of the time in the pharmacy store. Another one is incompatibility. Most of the times, the kinetics is applicable to the incompatibility of drug and excipient. In what rate they are getting progressing and degrading each other. Even though reaction is present, it takes 100 years to get degraded. It is not a botherance to us. That is the reason we apply the incompatibility also, what rate they are moving. Another one is the dissolution. When the drug product required to be entering into our body through the stomach, first it should be present in the solubilized state. So the rate of dissolution is producing the fast release dosage form, and a slow release dosage form, and the dissolution is slow, and it is acting long acting drug like that. So for the sustaining the release, we are doing a low kinetics and a low release. So kinetics is applicable to the dissolution also. Of course, we have got ADME, that is absorption, drug distribution, metabolism, and elimination. Most of the times, the drug absorption is having some rate. Through that, they will be getting absorbed through either skin or to the stomach or any biological membrane. And distribution to some rate, they will be distributed throughout our body when the blood is flowing. And drug action at the molecular level, and after that, they will be getting metabolized. So this is having some rate and elimination process. It means whatever the kinetics you are learning now, it will be applicable to all these things. But today the first topic, what is called as the stability, we are applying it. It means In 5th sem, 6th sem, 7th sem and 8th and your project work, you are going to apply all the bottom remaining 7. Remaining 6 also you are going to apply. But the concept is same, but only the difference is how we are going to apply and what factors that are predominant in the particular progress of the particular reaction. Most of the times, why do you study about the kinetics? Because it gives the light onto the mechanism of the changes. What is the mechanism? If it is getting affected, what is its mechanism? And also it allows the prediction of the degree of the change that will occur after a given time has elapsed, so that we can estimate self-life. So the resistance of the drug to the various chemical and physical microbiological reactions that may change with the original properties of the preparations during the transport and the storage and use. So during the transport, they will be undergoing different agitations. During the storage, they will be exposing to the different temperatures. And the usage, they will be exposing to the different environmental conditions. In all the cases, we are going to get a changes in the chemical and physical and microbiological manner. So they will be causing reactions. And most of the times it is linked to your self-life, and it is required to be quantitatively expressed as a self-life so that we will be able to draw the expiration period. This is actually what is our concern. Now the question comes, what is self-life? It is a time during which the medicinal product is predicted to remain fit for the intended use under the specific conditions of the storage. Most of the times, what is that stability is linked to the conditions of the storage. You know that now COVID vaccinations are coming, and 18 plus and 44 below, they are going to get a vaccination from the May 1 and May 1st, but it got delayed. You may be understanding that the storage condition is 2 to 8 degrees for that particular vaccination. If you are bringing large quantities without any storage, they will not be fit for use. They will not remain fit for use. It means we need to take care of due consideration during your transport, storage and use, all these sterilized conditions and your storage conditions. So this is a great logistic concern. We need to take care. So that is the reason you may be expecting that how that self-life is going to getting linked with the conditions of the storage. Generally, it is the time from the manufacturer or the preparation until the original potency or the content of the active ingredient has been reduced by the 10%. It means how much is the time it is taking to reduce it by the 10% and remaining 90%. So which is the limit of the chemical degradation? It means if anything product which is degrading more than 10% during the transit or storage and use, it is will not remain fit for usage. And we consider that period of degradation of 10% as our shelf life. If it is taking longer time, our shelf life is taking 10% degradation for 5 years, then we will be giving expiration dating as a 5 years. If it is 2 years, otherwise 1 month, then it will be a 1 month. But you need to link the shelf life with the storage condition. That is the prime concern. So this is what you need to understand. For that purpose only we are doing these stability concerns, and we are going to do the stability studies. Why do we study about the drug stability? The safety of the patient, that is the toxic product which is formed during the degradation, that is going to damage our patient. That is the reason we need to study the mechanisms and the toxic product nature. Another one is during the degradation, the initial content of the drug will be getting reduced. When it reduces to the below 90%, it will not act. That is actually another major issue we are going to look into it. Another one is we are going to meet the requirement of regulations. That is, after completion of B Pharmacy, you may be entering into the regulatory field like a drug inspector, where you are going to take the samples from the pharmacy store and from the manufacturing houses, and they will be sent for the testing. If they are not meeting the requirement of identity, strength, purity, and the quality, you can ask the company to close. You can ask the pharmacy store to close by putting the shutter down, and you can seal them. This is actually what the legal requirement. It is mandatory. It means whatever you are claiming on the label, if it is not present, and whatever the amount, whatever the name you are saying it, the drug, if it is not present inside the dosage form, and whatever the amount it is specified in the label, it is not present, and whatever the purity, it means you are saying it is containing 99% purity, if it is not having, and the quality, like it should not contain any added extraneous material and fibers and the dust particles, such things. So you will be having the quality requirement of your dissolution, fast release, slow release, whatever that. So if it is not meeting by any means, then you are going to have an authority to close the factory or close the pharmacy store without any hesitation. Because this is something relevant to our health of the personnel who are residing in the country. Most of the times, it is also helping us to prevent the economic repercussions, because if you are not having this, meeting the stability, and you are not fixing shelf life properly, your drug, whatever you are claiming on the label, it will be degraded in advance. So the patient will give the complaint, and that is a financial burden to the company to meet the fines which are imposed by the wrong giving of a dosage form and without any quality. So we need to pay the fine. That is very highly costly than our profits. This is the reason, in order to prevent all these economic repercussions, we are going to conduct this particular stability as a critical. Now you may be understanding that how our physical pharmaceutics is going to decide the life of the pharmacist, which is completely linked to the life of the drugs. And of course, we are achieving and linking to the life of the patients. The patient can be either our friend or our relative. It means whatever we are learning now, which is applicable to our kith and kin in nearby future. So whatever the damage which is going to occur, it is highly costly and highly emotional. So this is actually what the quality concern, and which is directly linked to the drug stability. And of course, you have got only one unit in the physical pharmaceutics in physical pharmacy 2, but it is not going to be sufficient. But you are going to have this topic repeatedly during your B pharmacy and M pharmacy, so that you will be having a complete understanding of this particular concept. Of course, we have got some practicals in this particular session itself. You will be able to assimilate how to fix the expiration date, what is the rate of reactions, how to determine them. These are all you will be able to know it. Even though you are not entering physically into the laboratory, we are going to provide you some of the data and solved problems, so that you will be able to understand what is its importance is. In the theory class itself, I am going to give you a little bit small problem, so that you can understand that how the rate and it is going to give the impact, how to calculate by using a small equations and small calculations and application of mathematical treatment. Most of the times, don't get confused with the rate and order. Both rate and order is very important. First, we will be taking the rate of reaction, then we will be entering into the order of reaction. Okay. So the rate is the speed or the velocity. So the speed, it is some pace it is moving, velocity it is moving in one direction. That is either it is a lower to higher, or higher to lower, or decreasing or increasing. So the speed it is moving in a small pace or faster pace of the reaction, with which a reactant or reactants undergo the change. This is actually called as a rate. So it is determined by the change in the concentration of reactant or a product with the time. So what we can do, how the reaction is progressing, either you can estimate the starting product, how it is decreasing, and ending product also you can take it how it is increasing. Both it will convey you how the reaction rate is progressing. So in our practical, we are going to do both, either that or this in our practical of our PP2. So the rate may be determined by the slowest rate, that is going to determine the pace of the reaction when two or more reactions are going. It means if you have got a multi-step synthesis, and whatever the rate it is slowest, which will decide your completion of your product. That is the reason we are going to consider the slowest one. If it is instantaneously, it is degrading. The moment you are taking the sample, it will degrade, so it is not your concern. But the slowest step is the rate determining step. What it will communicate? The rate of change of concentration, that is dc, divided by the t, that is dt, that is the unit time, is equal to, this rate is equal to directly, actually it is directly proportional to the concentration. But this directly proportional relationship, which is made into equality by using a proportionality constant, that is the rate constant, is called as a k. So this is actually what our fundamental equation is in the kinetics. dc by dt is equal to kc. The k is a proportionality constant, it is directly proportional to the concentration. This is actually what the rate is going to give by the k, but you have got c to the power of n, that is the power n is present in this particular reaction. This is going to give the order. So this we will be learning in due course of time. Now the order of reactions, the number of concentrations that determine the rate. Say for example, if k into c to the power of n, zero concentration of your reactant, no reactant is dependent, it is not involved. If it is a zero, then dc by dt is equal to k into c to the power of 0. Okay, k into c to the power of 0 means its first order reaction c to the power of 1. It means it is the rate of reaction is the change in the concentration per unit time. The rate of reaction is dependent on one concentration of your reactant, one concentration. If it is a 2, c to the power of 2, it is dependent on two concentrations of your reactants. Two reactants concentration is linked to your rate of change. It means that depending upon how many concentrations you will be having now, the order. So the zero order, it is not dependent on any concentration. The reaction is progressing immaterial of the concentration, how much it is present, whether it is a low or high. But in the c to the power of 1, it is dependent on one concentration of one of the reactants, it is dependent. And if it is a 2, two reactant concentrations are involved in that, that is deciding the rate. So the number of concentration of that determine the rate, it is giving an order. The way in which the concentration of the reactant influence the rate, so how much to the what extent it is also deciding the rate. How it is deciding the order and how the way is also it is going to give the impact, because we have got apparently it is appearing something in but in the background going something. So that's what we are going to learn in the order and the rate. Rate is the pace or the speed at which it is moving. The order is how many reactants are involved in that particular reaction. So rate and order of reaction, don't get confused. This is actually what the background is. Now, law of mass action is the fundamental you need to understand if you are understanding and studying any reaction. The rate of reaction is directly proportional to the molar concentration of reactants, each rise to the power of equal to the number of molecules undergoing that particular reaction. So if you see A into A, there are two reactants are present, A and B, and it is going to form a product. So this concentration of the A and B, that is the capital, which will be given within the square brackets, that is actually a concentration. So how many molecules which are involved, that is actually given by the A and B small. If it is a 2 molecules or 3 molecules. So in the law of mass action, you are generally studying in your intermediate stoichiometry or equilibrium, you are equalizing LHS and RHS, your reactant and the products. So this is what we are going to give. So in this particular case, the rate is directly proportional to, when you are taking that reaction, A into A is the number of molar concentrations which are involved into A plus B is the small b is equal to number of molar concentrations which are involved in the concentration B, and you are going to get a product that is given as a rate is directly proportional to the capital A to the power of A, capital B to the power of B. Sometimes A and B are equal, that is same. Sometimes it may be varying. That's what we will see later in the examples. So this directly proportionality constant, which will be taken into the equality, we are putting a k. That is actually called as a proportionality constant or called as a rate constant. Now the order of reaction is, the k is the rate of reaction and order of reaction is the sum of exponents. So the order of A is equal to A and order of B is equal to small b. The overall order is equal to A plus B. So we are going to get the order. Rate is given by the k. So this is what we are going to determine in this particular next due course of our time in the theory and the practical. Speed or the velocity of the reaction with which the reactant or the reactants are undergoing a change. It is determined by the change in the concentration of the reactant or the product with the function of the time. So we are going to see this, and we have already determined, and the overall reaction is A plus B, and the overall order of reaction is equal to A plus B, we have seen. Now we take the example. So we have got a acetic anhydride with ethyl alcohol to form ethyl acetate and the water. This is actually what the reaction is. And acetic anhydride and ethyl alcohol are the reactants. And you have got formation of the product is ethyl acetate. In this particular case, you are involving 1 molar concentration of acetic anhydride, 2 molar concentrations of your ethyl alcohol to get 2 moles of ethyl acetate and 1 mole of water in this particular reaction. If you want to draw the rate as per the previous one, we are applying the K, and 1 mole means the concentration of acetic anhydride to the power 1, and power 1 is equal to 1, whatever the concentration is the same only. Anything to the power of 0 is equal to 1, which already we have clarified. Here it is the power 1, so we are writing same thing. Whereas the ethanol, which has got power 2, so which is having a order of order for the concentration of acetic anhydride is 1, that is the first order. The order for the ethanol is second order. So this is actually the overall order is a third order. So it is, this equation is involving the third order. Now we will be having in a similar manner in our pharmaceutical industry, we are going to have so many reactants and the product which are going to decide our rate as a K and the exponents as a order, and more the order and the complexity will be more. This is what we need to see. The first thing and the simple and the one is zero order kinetics or zero order reactions. In the zero order reactions, the rate is constant and it is independent of the concentration of any reactant. It is not dependent. It is independent of concentration. Whether the concentration is very high or low, it is immaterial. The constant rate of reaction will be progressing. So the constant rate of drug release from the dosage form is highly desirable in our pharmaceutical dosage forms. We generally target this zero order in our pharmaceutical dosage form manufacture. This is our desired target, but it is very difficult to achieve. It is dependent on some parameters. It will give the trouble to pharmacist to invent a new delivery system with zero order. So the equation generally will be asked in the examination. Write the equation for the zero order and derive it. So in this particular case, a reactant A is converting into a product P with some rate called as a K, and it is involving A. If you are taking a rate constant, the change in the concentration with the time, because it is a zero order, it is equivalent to concentration of to the power of 0. So the concentration of the power of the 0 means that change in the concentration of A or the change in the concentration of the P is directly linked with the constant K, because C to the power of 0 is equal to 1, so it is constant. So the change in the concentration of either product or the reactant is constantly changing with the time. And in the case of reactant, it is when the reactant is progressing, it is keep on decreasing. So in that particular case, we are writing the minus term is the reaction is progressing and concentration is decreasing. That is the negative sign. It is showing here. So the dCd by dt is equal to K, and dc is equal to minus kt. So you are taking the denominator dt and it is dividing here, you are taking to the RHS, it is multiplying there, and dc is equal to k dt. It is minus, it is showing that the concentration is decreasing with the time, not increasing the time. Some rate of reactions, the reaction is progressing with increasing the concentration, then you have got a positive sign. Don't bother about now. We need to take a concentration as a modulus. We will see that. And if you are integrating from C0, that is the starting concentration, to Ct after a particular period of the time, what is the concentration in the particular limits? If you are integrating the DC, and similarly we are integrating with the starting time T0 and ending time as the Tt in the case of RHS time. So we are going to get the integral of upper limit and lower limit. Lower limit is C0, upper limit Ct dc is equal to integral of T0 at the starting of our reaction and T at the end of our reaction time T minus Kt. We are going to get integral of dc is equal to C, integral of minus k dt is equal to kt. So this is actually what our equation is. So you are applying the C and upper limit and lower limit when you are taking it. Upper limit Ct, so that is equivalent to a C, and minus C0, that is the starting, which is equivalent to T minus 0. T is the time T and T0 is equal to 0. So you are going to have a T and you have got a minus Kt. It means if you are applying the limit, you are after integral, you are going to get final concentration minus initial concentration is equal to minus Kt. This is actually what the reaction equation for zero order. It is a derivation which you will be asked generally. You need to represent with this. Now, when you are taking the same thing, the concentration on the y-axis and the time in the x-axis, this is what you are going to do in the practical. In the zero order kinetics practical, you are going to do the same thing. You are going to take a time with the minutes on the time axis and the C, molar concentration of your reactant on the y-axis. So it is keep on decreasing with the time. When the reaction is progressing, the reactant concentration is going to decrease. So the reaction equation in this particular case is, you are going to see the C0 is your initial concentration when you are taking, and C is the final concentration after the time T. You are going to arrive at C is equal to C0 minus Kt. If you are rearranging this particular equation, C is equal to C0 minus, because the minus C0 is coming to this side as a C0 and minus Kt. So this is actually what the reaction equation is. C is equal to C0 minus Kt, where it is appearing as a Y is equal to mx plus C. So in this particular case, Y is the concentration and X is the T. You have got the slope as a K and C0 is the intercept. In this particular case, slope is K is minus because the concentration is decreasing. If your product you are taking into consideration, it will increase. In that case, concentration going to increase. Either you can progress the reaction by taking the reactant or the product. In the case of product, you are going to get a positive value here. In the case of reactant, you are going to get a negative one. So you need to mention with units. What is the units for these K and T and C and your C0, everything. So now we are going to take in the units. So C0 will be given in the molar concentration, C is in the molar concentration, time in the time, that is in the minutes. K0, K will be given by the concentration per time. So this is concentration is mole per liter into the time, that is actually it is in the seconds. If your reaction progressing in the case of hours or minutes, you can put that in the hours and minutes also. But time can be given as a seconds if it is fast reaction is going on. So mole per liter second is the unit for the K. So this is actually molar concentration per second. It is going to change with the time. This is actually what the units of the K, that is zero order rate constant. We generally represent this as a K0. If you want to put a first order reaction K1, second order reaction K2, like that also you can do. So whatever representation for easy understand. Here we don't have any some more reaction rates, so we are representing it as by the K. how to determine the T off. If anybody is able to understand till